Hello everyone, Victor is here, your organic chemistry tutor, and since you guys keep asking me to make more substitution and elimination walkthrough videos, today I'm going to do just that. Here is the list of reactions I'm going to work through today, so grab your cup of coffee and notebook to work through these questions with me, hit the like button for good luck on the test, and let's get started. So if you're a little bit rusty on your substitution and elimination reactions, now it might be a good time for you to go and review those reactions before doing more practice. I will leave all links in the description below to the entire playlist. But if you feel comfortable with those, let's dive right in. So the first thing that I will always do, based on the predictive model that I teach in my predictive model video, I'm going to look at the nature of the reagent that I have. And in this case, I have this sodium azide. We have sodium, which is going to be our spectator ion, and generally we don't care about those ones. And we also have N3, the azide anion. And azide is an excellent nucleophile, and it is also completely non-basic, which means that this one is going to be something that we are going to put into the group of nucleophile-only type of a reagent. The next thing I'm going to look at is the position of my leaving group. Here, obviously, chlorine is going to be my leaving group, and we can see that that chlorine is in the primary position, or on the primary position, I should say. So, based on the predictive model, the primary position and the nucleophile-only type of a reagent means that we are looking at the SN2 reaction. So I remember that the SN2 reaction is a strict backside attack, the nucleophile going to displace our leaving group right away, and that also means that everything is going to happen at the same time, so we are not going to be forming any kind of intermediates. So if I were to jot down the mechanism for this reaction, the nitrogen of the azide is going to attack the carbon with my leaving group, the leaving group is going to get displaced, and in one movement in this SN2 reaction, I'm going to get the final product that's going to look like this. And of course, we didn't completely forget about our sodium from the very beginning. Sodium is just going to be a counter ion to our Cl-, so if you like, you could potentially draw those together as the pair of ions like I did, or you can say that this is a sodium chloride coproduct, and generally, since we don't really care about the coproducts, inorganic coproducts in our organic reactions, you could just skip that part altogether. Alright, moving to the next reaction, I have this in front of me. So step number one, I'm going to analyze my reagent, which is this pieces over here. That resembles anything that we have with the formula RO- and some sort of an alkali metal, in this case that's going to be sodium, as our counter ion. So that is an alkoxide. And alkoxide, as we know, it is a good base, and on top of that, it is also a nucleophile, which means that we are going to put that into the category of a base and a nucleophile type of a reagent. Next, I see that I have a secondary leaving group. My chlorine is sitting on the carbon, which is attached to only two other carbons. So if this is where my chlorine is, I have only two carbons attached to that carbon, so that is going to be my secondary leaving group. Based on our predictive model, we know that the base / nucleophile and the secondary position, they going to favor the E2 reaction. So for the E2 reaction, I remember that I need to have beta hydrogens. I will remind you real quick that for the E2 reaction, we have the leaving group, whatever that leaving group might be, and the nearby hydrogen, and that is this nearby hydrogen that we are going to be looking at. The position, the carbon where my leaving group is, that's going to be called an alpha position, and the placement of the hydrogen, that one is going to be the beta position, nearby position. In this case, the alpha carbon is going to be the one with the chlorine, and the beta carbon is going to be the one to the left, and another one to the right, like that. So in this case, the only place where I have beta hydrogens is going to be on the carbon to the right. So I will show that I have a hydrogen here, here, and another hydrogen over here. And since all of those are just hydrogens of the CH3 group, it really doesn't matter which of those three guys I'm going to pull off. Also, I will remind you that when it comes to the E2 reaction, our base, again, whatever that base is, going to come in, pull that proton off, and everything going to happen in the same cascade of the electron density, giving me double bond right away. So I'm going to end up making my carbon-carbon double bond just like that, and I'm not going to have any kind of intermediates in this case. So looking back at my example at hand, I will redraw both my starting material and my base. So what my base is going to do, it's going to come in, grab this hydrogen, move the electrons around to make the double bond, and the final product is going to end up with the double bond between the place where my chlorine is and the nearby carbon, which means that my final product in this case going to look just like that. And since the double bond that I have just formed is not capable of any kind of easy stereoisomerism, it's a terminal double bond, I'm not going to be worried about any stereochemistry here or multiple products. Also, since we do not have an option for more substituted versus less substituted double bond that we would normally consider for any kind of elimination reaction, here we are not going to be looking at that from the Zaitsev-Hoffman perspective because, well, there is only one double bond, so it's neither Zaitsev-Hoffman, we only have one choice and that's about it. So moving on to my next example, I see that I have the cyanide and I'm crossing out sodium right away because that's just a counter ion and I couldn't care less about its existence. So cyanide, Cn-, is a wonderful nucleophile and it is a completely non-basic, so that is a nucleophile only type of reagent. I'm seeing that I have two potential leaving groups. I have OMe and OTS. Well, here is the tricky part here. Your instructor can be a little bit mean in the sense that they are going to give you abbreviations like that, and that is your job to know what all of those abbreviations mean. Me stands for the methyl group, so whenever I see Me, I immediately think CH3. The TS abbreviation, that stands for the tosylate, so whenever I'm seeing that, I'm immediately thinking about this guy, which means that if I have O, Me, and OTS, only one of those is going to be the leaving group. Actually, for the tosylate, I already drew my oxygen because it's just this part that is going to be the tosylate without that initial oxygen. But for my CH3, I'm going to add that in, which is going to look like that. And we know that alkoxides in general, they are horrible leaving group unless they are, of course, protonated, while tosylate, that one is an excellent leaving group, which means that I'm going to go with the tosylate as my leaving group and I'm going to treat my methoxide as just something that is sitting on my molecule and not really doing anything. So, the next step in my analysis is going to be looking at the position of my leaving group. So the leaving group here is at the secondary position because that carbon, this carbon over here, is connected to two other carbons, so that is a secondary position. Based on our predictive model, secondary position, nucleophile only, so I have secondary position, nucleophile only, that is going to be an SN2 reaction. So for SN2 reaction, I remember that it has to be a backside attack, and if relevant, we are going to have the inversion of stereochemistry. Inversion of stereochemistry happens regardless, it's always going to happen. However, sometimes, like if we have a leaving group on the primary atom, we are not going to be showing that. In this case, however, we do have a very specific stereochemistry giving to our leaving group, which does mean that we are going to show the stereochemistry inversion here, and the cyanide, once it does the attack, is going to end up looking at us because our leaving group is currently looking away from us. So I'm going to redraw my reagents like this, and now when I'm showing my mechanism, I will show that cyanide comes here and attacks my carbon, that is my electrophile, and at the same time I'm going to be displacing my tosylate because SN2 reactions, they do not have any kind of intermediates, so we're going to be immediately kicking our leaving group out as we go with this reaction, which means that the product in this reaction is going to look like that. Notice that I did show my cyanide looking on the wedge, looking at me right away, because due to the inversion of the stereochemistry, due to the backside attack, we had to bring our nucleophile from the opposite side, from where our leaving group used to be. Alright, moving on, well, this looks like a fun reaction here. So the first thing that jumps at me right away is that I have H3PO4, which is an acid. And when it comes to acids, we are almost immediately going to be thinking about unimolecular reactions like E1 or SN1. SN2 reactions could potentially happen in acidic conditions, but those are gotta be, very special conditions in which we cannot form a carbocation, for instance, if let's say our leaving group is on the primary atom or something like that. But even then, tricks can happen, and carbocation rearrangements and formation of the carbocation can happen simultaneously and things like that. So SN2 or E2 reactions in acidic conditions, in other words, they are nearly impossible. The next thing that I'm seeing is that this is an alcohol. An alcohol plus acid, especially a non-nucleophilic acid like H3PO4, that is generally a good recipe for the E1 reaction. And when I say non-nucleophilic acid, I typically mean things like sulfuric acid, H2SO4, and phosphoric acid, H3PO4. Those two guys are going to be our two main non-nucleophilic acids. Things like HCl, HBr, HI, they do have the halide anion that we are going to make upon dissociation of that acid, and those negatively charged halides, they are nucleophilic. So in those cases, we are typically going to be seeing substitution reaction, but if we have a non-nucleophilic acid like sulfuric and phosphoric acid, we are most likely going to see the elimination reaction. And another factor that is kind of pushing us towards the elimination reaction here is the presence of heat. Whenever we have this little delta sign under our reaction arrow, or sometimes it can be even explicitly written out as heat, that means elevated temperature. And generally speaking, high temperature is going to promote any kind of reaction that increases the entropy of the system, and elimination is one type of reactions like that. So if I wanted to draw the mechanism for this reaction, I would start by showing both of my reagents, and step number 1 here is going to be protonation of my OH group with the phosphoric acid. In this case, that's going to create me a leaving group that is sitting on the secondary carbon. And since my leaving group in this case is on the secondary carbon, it means that the formation of the carbocation here is not that big of a deal. So I can easily have my leaving group dissociating and giving me the corresponding carbocation, which is going to look like this. And remember, as soon as you have a carbocation, you always need to check for any possible carbocation rearrangements. In this case, I have this as a secondary carbocation, and right next to it I have the quaternary position, which means that we can do the alkyl shift and make a more stable tertiary carbocation. In this case, there are two possible alkyl shifts that we can do in this reaction. One alkyl shift will have the part of the ring migrating over, and that's going to be essentially a ring expansion. So if I drew that one, my carbocation is going to look something like that. The other possibility here is going to be the methyl shift if I move the methyl group around. So if we look at that one, we are going to get a tertiary carbocation as well. However, generally speaking, whenever we are thinking about our carbocation rearrangements, we always want to look at the formation of the most stable carbocation possible, out of all options, of course. So in this case, I have a formation of a tertiary carbocation and a 6-membered ring over here. And in the other case, I have a tertiary carbocation with a 5-membered ring. Since 5-membered rings do have a little bit of an angular strain, a little bit of a ring strain, they're not as stable as 6-membered rings, which means that overall we are going to opt for the 6-membered ring, and we are going to discard our 5-membered ring here. Now, the next thing that we are going to look at is, do we have any other possible carbocation rearrangements after we have this one? Well, right now my carbocation is already tertiary, so it is unlikely to make another carbocation rearrangement happen. So what I'm going to do, I will look at the best position for my hydrogen to go away and make the most stable double bond possible. Because when it comes to E1 reactions, they typically follow the Zaitsev rule, which means that we are going to form the most stable double bond, which typically is going to be the most substituted double bond. Well, in this case, I have 3 options. I have a blue option over here, I have a green option that's going to be, let's say, there, and I have an orange option that's going to be over here. Out of all of these options, the blue one is going to be the best because it's going to give me the most substituted double bond. So if I wanted to show the mechanism for that, I would take this hydrogen, I would have our base coming in, and in this case the base is going to be the conjugate base of our acid, H2PO4-, so I will draw it as H2PO4- like that. Or another possibility is going to be H2O that we have just eliminated in the previous step. So either or, we are going to have those guys coming in, pulling our proton off, and that going to give us our final products, which in this case is going to look like that. And as I promised, the blue double bond that I have over here, that carbon, or those carbons I should probably say, are connected to 1, 2, 3, 4 other carbons, so that double bond is as substituted as it can possibly be, so that means that it's going to be the most stable double bond for this particular case. Alright, moving on to the next example, I'm still going to go through all my normal steps, looking at the reagent first. So CH3OH, that is our polar protic solvent. On top of that, that is also a poor base and a nucleophile. So looking at the position of my leaving group, the leaving group over there is at the tertiary position. So tertiary position, poor, base and a nucleophile, everything pushes me towards the SN1 or E1 reactions. The decision tree at this point is going to depend on our temperature. This reaction does not seem to indicate any temperature, which means that it is safe to assume that we are dealing with room temperature. And if there is nothing that pushes us towards one or the other reaction except for the temperature, the lower temperature or room temperature going to favor the substitution reaction rather than the elimination reaction. So mechanistically speaking, my step number 1 is going to be my leaving group dissociation. And once I no longer have my leaving group, I'm going to get the corresponding carbocation. In this case, that is already a tertiary carbocation, which means that the carbocation rearrangements are going to be extremely unlikely here. I cannot see anything that is better in this case. Every other option that I have is going to be either the primary position that I have nearby to it, or I'm going to have the secondary positions. So in other words, carbocation rearrangement cannot become a more stable carbocation here, and the rearrangement is going to be unlikely. So the next step, once I have my most stable carbocation in this case, is going to be the nucleophilic attack. The nucleophile in this case is going to be my CH3OH, my methanol, so the electrons on the oxygen are going to go towards my electrophilic carbon and make a new carbon-oxygen bond, giving me an intermediate like that. And when you guys are drawing these molecules, make sure that you're always showing your bonds. Show the new bond that you have made between oxygen and carbon. In our case, this is our new bond over here. Show the bond between oxygen and whatever alkyl group has been sitting on it. In my case, that is CH3. And do show the bond between oxygen and hydrogen. I cannot tell you how many times I see students just clumping it all together and kind of sticking onto that carbocation without showing any bonds. First of all, that's bad organic grammar. And as an instructor, if I cannot understand where your bonds are, what is actually connecting to what, I can assure you I would take points for that, and pretty much every instructor is going to be in the same boat with me here. Also, another thing, if you are not seeing bonds, then probably predicting the next step in your reaction or the next step in your mechanism is also going to be quite complicated. In this case, we have a positively charged molecule. It is a protonated molecule, so we are not particularly happy with that. Neutral molecules are generally more stable, that's why overall, whenever we are drawing our reactions in organic chemistry, we strive to make neutral molecules if we had neutral molecules to begin with. So in this case, I'm going to use another equivalent of my methanol, so another equivalent of CH3OH, that's going to come in and pull that extra proton off, giving me my neutral final product, which is going to look like that. Alright, moving on to the next reaction, the first thing that I'm seeing that in this case my reagent is H2O, and I will have the same problem here as in my previous example, where water is first of all a polar protic solvent And on top of that, there is also a poor base and a nucleophile. Then, looking at the position of my leaving group, which is the iodine in this case, I'm seeing that this is a secondary position, but that's not just a regular secondary position. This is also an allylic position because we are right next to a double bond, which means that we are going to deal with the resonance in this reaction. So, the allylic secondary position, poor base and a nucleophile, everything pushes us towards the SN1 reaction, and since we don't have any kind of heat involved here, then probably E1 is not going to be as big of a deal, but in reactions like that with allylic systems, the elimination is going to be present to a relatively large extent, so I'm going to say that this is an SN1 and it is also an E1 mechanisms that are going to be at the competition with each other. So to draw the mechanism, I'm going to start with my substrate, with my starting molecule. And the first thing that's going to happen here is the leaving group dissociation. And once my leaving group goes away, I'm going to end up with a secondary allylic carbocation. And as I've mentioned, this secondary allylic carbocation can experience resonance. So I'm going to show the other resonance structure right away that's going to look like this. So when it comes to your resonance structures, always make sure that you draw those resonance structures, because otherwise you can potentially miss the electrophilic positions in your molecule and come up with less possible products. So in the first case, if I'm just looking at the SN1 possible products, then I'm going to have water attacking my carbocation, so it can attack over here. So from the substitution perspective, I am going to end up with initially a molecule where my water is connected to a carbon. I have a plus charge on this water molecule right now, and then another equivalent of water can come in, pull that proton off, and I'm going to end up with my final product that looks like this. OH, and I'm showing the OH in a squiggly line here to signify that it can be either or stereochemistry because it is a chiral carbon, so in other words I'm going to end up with a racemic mixture here, or in other words the mixture of two different enantiomers, a 50-50 mixture of two enantiomers. If I do the same substitution style reaction for my other carbocation resonance contributor that I have here, I'm going to have water H2O attacking my carbocation from this perspective. That's going to give me an intermediate that looks like this. Again, I have plus on my oxygen. Another equivalent of water can come in and pull that one off, and I'm going to end up with the molecule that's going to look like this, and I have OH over here. Now, in this case, this molecule is not chiral, so we are not going to expect any kind of stereochemistry associated with that carbon. However, since we do have carbocations and we have resonance and things can potentially rotate there is a possibility of easy stereoisomerism around the double bond here, so you could potentially have the isomer that I just drew, or you could also make another molecule that's going to look like that. So the first one, the stereochemistry of the initial molecule that I drew there, that was my Z stereoisomer, and the one on the bottom, that is my E stereoisomer. So in this case, instead of the racemic mixture, instead of two enantiomers, I ended up with two diastereomers. Now, once you think that we are done, I'm also going to remind you that we also can have elimination reactions here. So to draw my elimination products, I'm going to redraw my carbocation, both resonance structures for it, and for the elimination part, I can either pull off one of these hydrogens, there are 3 hydrogens on the methyl group right next to my carbocation, or I can pull one of these hydrogens that are right next to my carbocation in the other resonance contributor, and both methyl groups on the right side are the same, so I'm not going to overwhelm the picture by showing all possible hydrogens. At the end of the day, they're going to give us the same product. So if I pull off the hydrogen in the first case, so I'm going to use, let's say, another equivalent of my CH3OH, but now that's going to be playing a role of a base, that's going to give me a final product that looks like this. In the other case, if I'm going to use my CH3OH to pull that proton off, I'm going to end up with the elimination product that's going to look something like that. So you're going to have a whole soup of different products in a reaction like that. You're going to have both substitution, you're going to have elimination products, and anything in between. And since, as I said, this is an allylic system, allylic systems do tend to give you hefty amount of elimination product, regardless of how much you might want to avoid those in the SN1 and E1 reactions. Alright, this one is a huge mess, so let's move on to the next example. Hopefully that one is a little bit more straightforward. So here, what I'm seeing is that I have my ethoxide as the reagent. That one is going to be something that we classify as a base and a nucleophile. We have already seen something similar to that today, but that other example had one carbon less. The next thing that I'm going to look at, as always, is going to be the position of my leaving group. In this case, the position of the leaving group is the secondary position, so base and a nucleophile, secondary position, everything pushes me towards the E2 reaction. So I remember that in the case of the E2 reaction, my leaving group, so if I have a leaving group over here, and I have my hydrogen on the other carbon over there, the leaving group and my hydrogen must be antiperiplanar or trans to each other. So if I check out the leaving group in this case, that is my bromine, which is looking away from us. The only hydrogen that is available to us right now is going to be this guy hiding behind the phenyl group, and it also looks away from us, which means that in a case like that we have a little bit of a problem. And the problem is that our leaving group and the hydrogen are not trans, they are not antiperiplanar to each other. So what are we going to do about that? Well, we are going to rotate part of the molecule around. Let's say I rotate the left side of the molecule around, which is going to give me a molecule like that. If you're having trouble manipulating your molecule in space, make sure you draw the Newman projection, or better yet, build the molecule from your molecular model kit and rotate it around to see where exactly the atoms are. Well, in this case, now my hydrogen and my bromine are indeed antiperiplanar to each other, so when my base comes in, and for my base I have this ethoxide over here, or if you like to draw it in a line structure, we'll draw it like that. So when this guy comes in and pulls on my hydrogen, causing the cascade of the electron density, making a double bond between these two carbons, I would end up with a double bond right there, and that double bond is going to specifically have the phenyl group that is going to look away from the rest of my molecule. That is going to be, in this case, an E isomer. And if you didn't pay attention to the fact that the leaving group and the hydrogen must be antiperiplanar to each other and just went on with this reaction and drew your final product looking like this, where your phenyl group is on the same side with this three-membered ring like that, well, that would be a problem because this product cannot be formed. So since we don't see that one, if you were to put something like that on the exam, that would definitely be counted against you and you would lose points on that. The Z product in this case is not going to be formed in any appreciable amount, and our actual product is going to be the E product. Now, also don't make a faulty assumption that it's always going to be the E product. You have to analyze your structures, because otherwise you can easily fall into a trap where the Z maybe is a major product or something like that. So don't just go with the flow and think that, I'm going to spread my things as much from each other as possible and just make the most stable product. That's not always going to be the case. Analyze your molecule, and based on your analysis, only then draw the final product. Don't just assume what the product is going to look like. These are very common things that instructors are going to target in the tests, and they are going to catch you on that if you are not paying attention. Now, in my last example over here, I again have CH3OH as my reagent, and we have already seen that before. That is going to be a poor base in a nucleophile, and it is also a polar protic solvent on top of that. We have heat, And we have a secondary position for our leaving group. Based on the predictive model, all of that is going to push us towards the SN1 or E1 style reactions, and we know that since we have the higher temperature here, we have elevated temperature, we are most likely going to look at the E1 reaction here rather than the SN1 reaction. So mechanistically speaking, I will, as per usual, redraw my starting material and start with the leaving group dissociation like any unimolecular reaction would start, which gives me a corresponding carbocation. Now, this carbocation is secondary, it is at the secondary position, and right next to it we have a tertiary position. So again, that means that we are likely to have some sort of a carbocation rearrangement. And in this case, we have two possibilities. Possibility number one is going to be the hydride shift. So if that were to happen, then I would end up with a 5-membered ring with a tertiary carbocation like this. The other possibility here is going to be the ring expansion, that's going to give you a 6-membered ring, which is going to look like that. It's going to give you a secondary carbocation, but on a 6-membered ring, which is generally more stable. So the problem here is that different instructors treat these carbocation rearrangements slightly differently. From the research data, we know that in this case the ring expansion is actually going to be somewhat more favorable than the formation of the tertiary carbocation. However, if your instructor strictly adheres to the rule that we always want to go to the more substituted carbocation, then you would want to go with the formation of the tertiary carbocation. Because of that, I will analyze both possibilities in this case. So if I go with my green possibility where I form the tertiary carbocation, this guy, then from this point I can form two major products. One, which is going to look like this by pulling off this hydrogen, and another one, which is going to look like that if I pull either this or that hydrogen. Since the molecule is symmetrical in that sense, it doesn't matter which of those two I'm going to pull off. In the case of the blue carbocation, my secondary carbocation, I'm actually going to have another carbocation rearrangement to give me a more stable tertiary carbocation. So overall, I'm going to end up with a tertiary carbocation that looks like this, and from this point I can again make two different products. One product is going to be by eliminating this hydrogen, and this product is going to give me a double bond kind of poking outside of my ring like that. And another one is going to be by eliminating one of these two hydrogens. Again, the molecule is symmetrical, so it doesn't matter which one you grab, but in this case, we are going to make a product that looks like this. If we go with the blue method, then our major product is going to be the more substituted double bond on the 6-membered ring like that. If we go with the green method, well, in this case, both double bonds are pretty much the same substitution-wise. Both of them are attached to 3 other carbons. The one within the 5-membered ring is a hair more stable than the other one, but again, unless you guys talk about those small distinctions in your course, there would be no way of you knowing that. So for the purposes of just a regular course, we would say that both green structures are more or less the same, and we would say that both of them are our major products in this case. Well, what do you guys think about these questions? Did you like them? Did I catch you on any of these, or did you get all the answers correctly? Let me know in the comments below, and I would love to hear from you. Also, if you have any questions, suggestions, or feedback, please tell me about it in the comments below as well. Subscribe to the channel for daily organic chemistry updates, watch this video next to learn more awesome stuff about organic chemistry, and I will see you tomorrow.